about combustion reactions. And I'm gonna. Hey, we're working finally. I've been having just endless technology problems. Sorry? Oh, I was so annoyed. After you guys left, I threw it across the room, actually, and now it's working. So figure that out. Anyway.
Have you found the keyboard yet?
I don't want to talk about my keyboard. See, I don't know what to do because I found one on Kijiji I can buy, but my problem is this. I'm a cheapskate, and I know for a fact that the instant I buy a new one, there'll be an email in my inbox saying, hey, we found your keyboard. And then you know what I'll have? 2 keyboards, which is exactly useless. I don't need a spare. I don't want a spare. I want my keyboard, the one I have. So I'm going to carry this to and from home, but leave like the tiny little thin keyboard that is magnetically attached to it, one in each place. That just seems wasteful. And it's a protective cover that keeps the screen from getting cracked. So like I would be putting this at more risk so I could have a keyboard in each place. That just doesn't seem practical.
But you could have a spare in case you lose it again.
And then detach it. Don't use it. That's just my transportation keyboard. But they're not cheap. Like I found a used one for $40, so that's not bad. But new, they're like $150. That's a lot of money.
No, not at the mall. If they have one at the mall left, like half off.
Oh, really?
Yeah.
Well, that's good. Which mall? Seaway Mall?
Yeah.
I like that Seaway Mall because they have an electric car charger. No, I do. I think that's great. So on Wednesdays when my daughter goes to dance, I always go there and charge my car. And it's like, man, I just got like 75 cents worth of power for my car for free. So you think like that's half my coffee. I bet now I've basically had a 75-cent coffee. That's pretty good, right? Anyway. As I was saying, I'm a cheapskate. But no, I don't think I am a cheapskate. I have no problem spending money on things. I just think if you spend less money on individual things, you get to do more things. Right? Does that make sense? Like if every time you do something, you find a way to make it a little bit cheaper, you then have more money to do more things. Anyway, this is my theory. So we're going to talk about combustion reactions. What's a combustion reaction? Yeah, fire. Fire. Not necessarily an explosion, but fire. For example, when we use the Bunsen burners, that is a combustion reaction. Make sense? We are taking the gas, the natural gas that runs through the pipes, and we are combusting it. Specifically, that means reacting with oxygen. So combustion is a reaction with oxygen, but it's distinct in that it is a fast, energetic reaction with oxygen. Does that make sense? So when your car rusts, that's also a reaction with oxygen, right? All rust is iron oxide, but that's not combustion. So combustion is a reaction with oxygen that happens quickly and energetically. Does that make sense? And we can write that. I'm going to write that. You can do what you like. Quick, energetic reactions with oxygen. Now, of the elements in the universe that are common, of the elements that there are a lot of in nature, oxygen is by far the most reactive. Or I should say in our particular nature, in our atmosphere. Because hydrogen is very reactive, but hydrogen is so reactive that we don't find hydrogen gas in our atmosphere. It reacts right away. Does that make sense? But oxygen is very, very reactive. It likes to react with things, as does chlorine, fluorine, bromine. But chlorine, fluorine, and bromine aren't in big concentrations in our atmosphere. Whereas oxygen, does anyone know off the top of their head what percentage of our atmosphere is composed of oxygen?
It's like 30 something.
I think it's 20-something, but it's high. I believe nitrogen's roughly 70-some%, oxygen's roughly 20%, and then carbon dioxide makes up something like 1 or 2%, and then everything else is just trace amounts.
Oh, I thought carbon dioxide was 5%, and everything else was trace amounts.
I mean, you may be right. I'm doing this from memory when I easily could have looked them up before the lesson and then known them. But point being, of the elements that we come across in nature regularly, oxygen is very, very reactive. How could I know that looking at oxygen on the periodic table, by the way? What do we know about it? Yeah.
That because it's farther to the right that it's more reactive.
Good. Yeah, it's very electron hungry. It's always looking to steal electrons. And that makes sense, just like you say, because it's to the right of the periodic table. If you remember, the further to the right we go, the higher the electronegativity gets, until we get the noble gases, which aren't electron hungry at all. So oxygen is very reactive, which means this. When oxygen comes into contact with things that can react, it does so. And it tends to do so quite quickly. Especially if you ever have like a high oxygen, an oxygen-rich environment. For example, has anyone heard of the Apollo 1 disaster? What is the Apollo program? Does anyone know? Yeah, so it was in the 60s. I believe the Apollo program started in 65. It was the series, or 63, sorry. It was the series of launches aimed to eventually land man on the moon, and they did. Apollo 11, the 11th mission in the Apollo program, actually put people on the moon, brought them back, and returned them. The first Apollo mission, which was just designed to be a test of the Saturn V rocket, which was the rocket they were using in that program, ended in disaster because not on launch day, not in space, but just a day when they were doing a pressure test of the cabin. So they had it on the launch pad, and the astronauts went into the capsule, dressed like they would be for launch, but there was no launch planned that day. But they pressurized the cabin. And at the time, they used a really rich oxygen mix in the cabin. And the reason for that being because even though they had scrubbers for CO2 to get CO2 out of the air and scrubbers to get carbon monoxide out of the air, they wanted to make sure that nobody could suffocate, because that's still not as good as having big open spaces on Earth and plants and things like that. So they made it an oxygen-rich environment, so much so that that things that we don't think of as being flammable, or at least especially flammable, in oxygen-rich environments become very, very flammable. As it happened, there was a tiny spark in one of the electrical components, and next to it, all throughout the spaceship, they had Velcro, which they still do on spaceships, because in free fall, up above Earth's, outside of Earth's, well, it's not outside of Earth's gravitational field at all, but free from Earth's gravity the way we normally experience it, things just float away. So they have Velcro all over the place, so they can just stick things to the wall and they'll stay there. Makes sense, right? There's a small little spark in this Velcro that on Earth we would never think of as being flammable under normal conditions. In an oxygen-rich environment, burst into flames immediately. And there was so much oxygen in the cabin that in a matter of seconds, everything was in flames and 3 astronauts were killed. But it's because oxygen is very, very, very reactive. So today we want to talk about specific types of combustion. To be clear, you can burn all kinds of things. And we're going to do a couple little demonstrations of that on Monday, which you've probably done before, burning magnesium metal, burning copper metal, things like that. Is that familiar? Something we've done before? No? Oh, good. It'll be fun for you. It's a fun one. But today I want to focus on combustion of covalent compounds. And specifically, I want to focus on the things we most commonly burn, which are called hydrocarbons. What's a hydrocarbon? Very good. So we're talking about compounds made out of hydrogen and carbon. And they follow this basic form. We have something that's made out of carbon and hydrogen. And I'm going to put an X and a Y here to say that we can make any possible hydrocarbon. Does that make sense? By X, I mean that could be any number. And by Y, I mean that could be any number. So anything made just of carbon and hydrogen can undergo a combustion with oxygen. Now, maybe you know this because one place we very regularly do this is, if you drove to school on some sort of automotive device today, you underwent this reaction. Gasoline, our fuel, is all made of hydrocarbons. It's made of a bunch of different hydrocarbons. Yep.
You forgot to label what state of matter it is.
Yeah, we'll get that. It could be any number of states of matter, because some hydrocarbons are liquid, some are solid, some are gas. Okay, so what would it be? Very good. What gets produced when we combust something made of carbon and hydrogen? Yep. Okay. And heat, for sure. Good. Why is that? Because you're right. Carbon dioxide, definitely heat gets released, but carbon dioxide and water. Why is that? What's actually happening? What do you think? Oh, that's okay. What do you think? Yeah.
We're every hydrogen, so for every, because we can have any number of hydrogens or carbons, eventually two hydrogens can be paired up with one of the oxygens to form a fuel.
Yeah, I want you to think of it this way. Oxygen, and this is actually how it happens, oxygen collides with these molecules and literally rips them apart. Right? It's like if you have a little sibling who used to get into your Lego and they just rip every single piece apart. Oxygen gets in there and will take that hydrocarbon and rip it apart completely. So it will separate every carbon from one another, every hydrogen from one another, just leave them loose. And then what gets stuck to all those carbons and all those hydrogens? Oxygen. Oxygen sticks itself to them. Does that make sense? So this is called oxidation. And in combustion, it happens quickly. So the goal of oxygen is always to fully oxidize this thing. It's to take all the carbon and all the hydrogen and stick it to oxygen. Oxygen likes being bound to those more than it likes being bound to itself, because when it's bound to itself, its big electronegativity, its strong pull on electrons, doesn't give it any advantage because it's pulling against something just as strong as itself. Does that make sense? But when oxygen binds to carbon, and especially when oxygen binds to hydrogen, now it really has the upper hand in electronegativity, and it can make a polar bond. Does that make sense? So oxygen would much rather be bound to carbon and to hydrogen. So under normal conditions, this is ripped apart completely, and every carbon ends up with oxygens. And of course, we know carbon can make how many bonds? What's its carrying capacity? Yeah, carbon can make 4 bonds because it wants 4 more electrons. How many bonds can oxygen make? 2. So we get carbon in the middle, making a double bond to this oxygen and a double bond to that oxygen. And that way both oxygens make 2 bonds and the carbon makes 4. So it makes carbon dioxide and it makes water. By the way, what states of matter will this be in a combustion? Yep.
The CO2 is a gas.
Yep. Well, in a combustion, what do you think the H2O is? Yeah, what temperature does water turn into a gas at? 100. Do you think most flames and most explosions are above 100 Celsius? Definitely, right? So in this case, everything should be a gas. And that's your experience. You probably don't see the water coming out of your car, right, out of the tailpipe.
Unless it's wintertime and you see it.
Yeah, sometimes it's true. Sometimes in wintertime, you'll see some water dripping out of it, right? But in general, we see it in gaseous form. And this again looks like that. Now, obviously, you would then have to balance this. And I'm just going to put random letters here to show that how it balances is going to depend on what? Exactly. How this thing balances will depend on what that hydrocarbon was. So I want to do an example. Methane is the simplest hydrocarbon, and it's literally a carbon. How many bonds does carbon make? 4. And on each of those, we're going to put a hydrogen. And how many bonds does hydrogen make? Just 1. So that's happy there. So methane has the formula CH4. And I want you to try completely combusting that. React it with oxygen. And the nice thing about this is before I do any work whatsoever, I know what the products are going to be. What are the products? CO2 and water. Very good. So I want you to balance this. Almost there. Hydrogens are balanced, carbons are balanced. Why? Well, how many oxygens do you have over here? Do you know what you're doing to balance this? Well, let's take a look. So we have one carbon here. How many carbons do we have here? 2. That 2 is on the oxygen, right? How many carbons? Yep, so carbon's good. Now how many hydrogens here? Okay, and how many here? So what do we have to do here? Well, it's already got 2, so we have to put 4 in front. Yeah, good. Yeah. And now that 2 affects both. So how many oxygens do we have here? Because again, that affects the whole thing. So we have 1 and 2. And how many here? The total 4 on this side. How many do we have over here? Good. So what do we need? Very good. Excellent. Great job. Okay, so it seems like everyone was able to balance this pretty quickly, which is great. What do we have to do? What do we have to do? Yeah.
Put a 2 in front of the H2O so that you can balance the hydrogens.
Nice.
And then a 2 in front of O2 to balance the oxygen.
Very good. Great. Does anyone have any questions about that? That's pretty straightforward, yeah? The nice thing about combusting a hydrocarbon is you always get the same products, right? So let's try this next one. Pentane. Pentane. What are my products going to be again? CO2 and H2O. Great. Nice. If I'm not mistaken, pentane is a liquid at room temperature. I should probably look that up to be sure. Oxygen's a gas. Carbon dioxide's a gas. And water in this form will be a gas when it's released. Oh, it feels so good to be mobile again. I'm trying to remember the first year of my teaching career, I used an overhead projector a lot. And I just try to imagine going back in time and being like, oh, I've got to erase something. It just seems so primitive. So can I ask you guys, what is your first step in balancing this? There's no right answer, but I know what my first step would be. What's yours?
Put the 5 on CO2.
Yeah, I think I like that too. Why do we like that?
Because a carbon only appears once in both sides, so it'd be sort of easy just to get that out of the way.
Yeah, so I feel like that we can just know that that's balanced, right? Nice, I like that. Where did you go next? What did you do next?
I started with hydrogen.
Okay, so what did you put in first then? Perfect, so you put a 6 there. Did you do the carbon next? Did you put the 5 in after that?
Yeah.
Okay, yeah. Great, and how did you know this had to be an 8 now?
Because there was 5 in front of the CO2, and that means there's an oxygen there.
Great.
And then if there's a 6 in front of the H2O, that means there's 6 oxygens there, which means 6. So then 2 times 8.
Great, yeah, that's perfect. So these can be somewhat tricky to balance, but that was doable, yeah? Yeah, that's good. Yeah, Did everyone? I guess everyone couldn't possibly have seen because everyone isn't standing exactly where I'm standing. But yeah, very good. You don't have to draw this, but what's this look like? Well, it looks like 5 carbons in a chain. And then how many bonds does every carbon have to have total? Yeah, and so what am I just going to put on all of these? Yeah, and that just works nicely. I didn't have to do any double bonds or any messing about. Oh, sure I could. I would just have to lose hydrogens. So this is, sorry?
That make a new thing?
Yeah, it'd make Pentane. Just wait, organic chemistry, you're going to love it. And everyone who's in the 4C right now, you're going to get to do an organic chemistry unit last unit, and it's actually really fun. I really like the 4C organic unit. And then if you're planning to take the 4U next semester, you'll do a whole unit on organic that is fun, and then a second unit on organics that is really fun, but also pretty challenging. But, no. I love it, but it is tricky. Anyway, that's great. So again, the thing to keep in mind is that in combustion, oxygen goes and it rips this whole thing apart. It breaks every single one of these bonds, and it bonds itself to everything that's left behind. Does that make sense? So an oxygen just comes here and makes these bonds. Comes here and makes those bonds. Come here and makes those. Oh, not there. And then oxygens go here, and here, and here, and here, and here. So oxygen just completely fills in all the gaps. You don't have to draw that, but does that kind of make sense? Now, by the way, the more chemistry you study, the more you learn that oxygen's a real bully. He does. He shakes down every other element he can for the lunch electrons. Who does he like shaking down better? Oxygen or carbon or hydrogen? Who's a better mark for oxygen? Sorry? You're right. How do you know that? What do you think? What do you think? Yeah. So hydrogen's weaker. Hydrogen's easier to steal electrons from, and carbon or oxygen, being a bully, likes to pick on the small, the weak. Yeah. The thing, yep. Yeah, I like that too, right? Like one oxygen can bond to 2 hydrogens, right? Whereas it takes 2 oxygens just to bond to 1 carbon, right? So like when Kevin goes out to beat people up at lunchtime, he doesn't want to find big grade 9s that he has to get a second person to beat up. He likes the little ones where he can beat 2 of them up at once, right? What I'm saying is Kevin's a lot like oxygen. And grade 9s are a lot like hydrogen. And I've reported you to the police, so. Hi, Miss Sargent. I assume she's listening right now. You're going to hear me get paged in about 1 minute. Mr. Len, like Mr. Smith's going to come in and just carry on the lesson right where I left off. And you'll never see me again. Yeah, that'll just be it.
Wait, this.
An unnamed teacher with the DSPN. Anyway.
Is there a live version that you see somebody watching right now? Is that why you're making the joke?
No, I'm making the joke because I'm saying inappropriate things. Here's why I say this. Let's imagine that Kevin and a bunch of his buddies, let's say he's got like the whole grade 11, grade 12 cohort, all the seniors. He can beat up all the grade 9s, right? And all the grade 10s because he's just got tons of friends. But now let's imagine that Kevin's numbers are limited. He's just got a few friends. Who's he going to pick on? The slightly bigger, tougher guys or the weaker, smaller guys? What do you think?
Smaller guys just beat more.
Yeah, knowing Kevin as I do, I know that he's going after the wee little ones. Like maybe he'll just go to the elementary school. You're like, listen, kid, give me your quarters. Hi, Miss Sargent. So, yeah, is she really? That's disappointing. Listen. Let me tell you about the time I told made the director of education a part of my swingers party lesson. I'm past shame at this point.
I don't know what that is.
Anyway,
You don't
that's
want to
for the
know.
best. Anyway, that's how I used to teach double displacement reactions. So anyway, here's what happens. In a perfect world where we have enough oxygen, what I just described to you is what happens. Everything gets ripped apart. All the carbon ends up with oxygen. All the hydrogen ends up with oxygen. Does that make sense? But we also have a situation called incomplete combustion. Let me ask you this. In your house, hopefully, and if you don't, you should fix this weekend. But you probably have in a number of your outlets plugged throughout the house, or maybe you have more modern smoke detectors that have them built in. But you probably have in your home what detectors? And they're usually plugged into an outlet somewhere. Carbon monoxide. What's carbon monoxide?
Stuff that makes you die.
Yeah. Carbon monoxide is dangerous because the hemoglobin in your blood actually likes carbon monoxide way better than it likes oxygen. So the hemoglobin in your blood is a molecule that's designed to bond to oxygen. So it flows into your lungs. There's oxygen in your lungs. It grabs the oxygen, flows to all the parts of your body, and delivers that oxygen for you to use. That's hemoglobin. That's why you have iron in your blood, because the hemoglobin molecule requires iron atoms to work. But the problem with hemoglobin is, much more than it likes oxygen, it loves carbon monoxide. And even worse, it's really good at sticking to carbon monoxide, not so good at letting go of it. So you can be in a room full of oxygen and suffocate to death. Literally suffocate, which means not get oxygen, if also in that room is even just a little bit of carbon monoxide. Dangerous stuff. And it's odorless. It's colorless. So that's why we have detectors. Very important. It's important because your house has something in it, at least one thing, and probably two things in it that are constantly burning hydrocarbons. What are those things? Furnace, and for most people, don't know, hot water heater? Most people's hot water heaters are gas-fired as well. Some people have electric ones, but most people's hot water heaters are gas-fired. If combustion happens properly, it produces water and carbon dioxide. And even if that leaked into your house, obviously too much carbon dioxide is dangerous, but it takes a lot of it to be dangerous. Carbon monoxide, though, just takes a little. And here's why would we get carbon monoxide? We don't even know how to draw a Lewis structure for carbon monoxide. You have to take grade 12 university chem to figure out why that even works. But let me ask you this too. If I take a log, which is basically made of carbon, hydrogen, and oxygen, and I burn it, does it burn away perfectly, making just CO2 and water? What do you see left over from that log? Ashes. And what are ashes? Carbon. So what would you say? Yeah, you're totally right. You're totally right. But specifically, it's just carbon. Ash, pure ash is just carbon. So here's what happens. If there's not enough oxygen around, what does oxygen like better? The hydrogen. So it's always going to go to the hydrogen and make water. And if there's not enough oxygen left over, it may, instead of making CO2, just make carbon monoxide. And if there's really not much oxygen, it may not even make carbon monoxide. It may just make carbon. The oxygen will just ignore the carbon, and it will bond with the hydrogen because that's a more favorable bond. Does that make sense? And you've all seen this. If you've burned a piece of wood, you know that you're left with just carbon. Interestingly, you could take that ash, and if you added a bit of oxidizer to it, you can actually burn the ash from a fire. And if you do that, eventually you will end up with just CO2, just water, yeah. In the fire pit itself, you'll have nothing. So if you took a fire pit's ash and added oxidizing material and ignited again, eventually you'll end up with nothing. That carbon can be burned away. But under normal conditions, there's not enough oxygen present for that to burn away. Does that make sense? Yeah. Yes, but now you're talking high temperatures. And you'll still end up, you will end up with oxides, so you won't end up just with a gas. You'll still have something solid there. It'll just be something new, something different. You'll end up with metal oxides. But yes. Like really, like you burned copper this day in lab, right? So you burned metal. Rocks are just metal alloys mixed with already oxidized materials and things like that. So yeah, you can burn rocks, but usually now you're talking high temperature. So when there's insufficient oxygen present, carbons will react with oxygen to form some combination of carbon dioxide, carbon monoxide, or solid carbon. So it looks like this: CXHY, in other words, some hydrocarbon plus oxygen will give us still water. The hydrogen is always going to end up making water. But now we'll get some CO2, or maybe none. The number in front of that could be 0. We'll get some carbon monoxide and some solid carbon. And again, I'm going to just show here that could be any combination thereof. More oxygen will favor CO2. Less oxygen will favor carbon monoxide, and even less oxygen will favor just solid carbon. Does that make sense? This is kind of esoteric because there's no one answer to these. In fact, the mathematically among you should know that there will always be how many possible right answers? Infinite. There's literally, when you have an equation like this where you can make the parameters whatever you want, there's an infinite number of solutions to these. So if I give you a question about incomplete combustion on a test, you can answer it any way you want. As long as it's balanced, it works. Does that make sense? As long as it's balanced, it works. It can be true. So I have given you ethane, which is C2H6, and I want you to give me 2 different incomplete combustions that both work. So you can fill it in, and you don't have to have all 3. If you wanted to just have CO2 and carbon monoxide but no solid carbon, that's okay. If you want to just have solid carbon, that's okay. So in other words, these numbers could also be 0. You could make no CO or no CO2. As long as it's balanced, it is a valid solution. So I want you to give me 2 valid solutions. And we should all have something different. Well, I mean, maybe you'll end up with the same thing. But likely you won't. So I want you right now to come up with 2 solutions that work. I'm going to make my own. Okay. Don't copy me. Yeah, just don't copy me. That's like saying, Orlando, you should lock up your lunch money. Be like, or don't steal from me. How's that? She's like, yeah, that's not going to happen, buddy. Good, I like this. Yeah.
Is ethane a gas?
Ethane is gas at room temperature. Thank you. Good question. If I'm remembering right, and I'm likely not, but butane, which is C3H8, is the first one that is liquid at room temperature. Like if you have a butane lighter, I think that's typically a liquid inside it. But I'm not 100%. I'm not confident in that.
You have big numbers.
Yeah, I wanted to be a little crazy.
You're having way too much fun with that 5 and 5 CPU H6. Oh, and now you can. That's not a nice number. Don't like that number.
Okay, can I share a couple of my solutions? And then I want to hear yours. So my first one, I thought it would be fun to stick myself with big numbers and then have to make it work. So I just started by putting a 5 in front of this. So I said I had 10 carbon and 30 hydrogens. Does that make sense? I just thought, like, okay, I can do that. And then I just picked randomly here so that my carbons added up to 10. So I said 5 carbons by themselves, 1 carbon monoxide, 4 carbon dioxide. Does that make sense? And then I just counted my oxygens. Oh, and sorry, I had to make hydrogen work. And how many hydrogens do I have over here? 5 times 6 is 30. So what number do I have to put in front here? 15. Does that make sense? Tell me if it doesn't. Good. So then I just counted my oxygens. So I said my 15 waters gives me 15 oxygens. My 4 carbon dioxides give me 8 oxygens. And my 1 carbon monoxide gives me 1 oxygen. And then my 5 carbons doesn't give me any, right? So that all adds up. 15 and 8 is 23, and 1 is 24. So what number do I need over here? 12. Make sense? Yeah. Do they not? Yeah, that's 10, right? So here's 4 carbons. Here's 1 carbon. And then I have 5 carbons all by themselves here. No problem. Do you see that? That's okay. Do you see that one there?
Yeah, I will look at the 5.
No, yeah, no problem. So that's 10 carbons total. But no, that's good. Those are the questions we want to be asking. Make sure you get. So does that solution make sense? Now I did another one, and I made my life really miserable because I put what number in front? No, don't worry about the fraction yet. What number did I put in front? In fact, let's hold off. We'll come to this. So just to challenge myself, what number did I put in front of my C2H6? A 7. So how many carbons does that leave me with? 14. But you know what I did? I thought, you know what? I take it back. I don't want to be brave. So I just went over here and said 14 carbons. Is that a fair solution?
Yeah.
Yeah, you bet it is. Hey, I'm done. Now I just need to make the oxygen hydrogen work. If I have 7 times 6, how many hydrogens is that? What's 7 times 6?
41.
42. Good. So I have 42 hydrogens. So what do I have to put in here? 21. Okay. Now I've just got to make the oxygens work. How many oxygens do I have here? 21. Now I'm going to tell you about a rule they let us break. And they only do it for combustion, and they just do it so that we don't have to write big, stupid numbers. You're only allowed to do this for combustion, and they shouldn't let you do it because it's a big cheat. All right, it's cheating. Here's what they let us do. The problem is, can I multiply 2 by anything to get 21?
No.
No, right? So instead of doubling the whole thing, and again, you can only do this for combustion. You don't get to do it anywhere else. They let me just cheat and say 21 doesn't work, but 21 would work if I divided it by 2. Okay, it's a cheat. I don't like it. In my mind, we'd be better off doubling this whole thing, but this is allowed. You will see it in textbooks. You'll see it in reactions. You will see it published, so I want you to be aware of it. Okay? Which is sometimes we use, I'm just going to say some number over 2 fractions with oxygen. For balancing. It's skeezy, but it's allowed. I'm going to write that. Does that make sense to everybody, that fraction? Tell me if it doesn't, because I'm happy to try explaining it again. It's just a math cheat. Because O2 is diatomic, it needs to come in even numbers, 2, 4, 6, 8, 10, 12. If we need an odd number of them, they let us just divide by 2 and cheat. When the reality is, I would actually have to double this whole thing. So, yep. Mathematically, that's the exact same answer. In practice, that's not permitted. So in terms of the math, you're completely right. It's the exact same number. But in terms of the chemistry, they let us write this because do you know what this really means? This is telling a chemist that in reality, this whole reaction has to be doubled. So the real reaction it's describing looks like this. 14 C2H6s plus how many O2s? 21 O2s gives me, what's going to be the first thing here? 42 waters and good. Does that make sense? That fraction is giving me a hint that in reality, this whole reaction is doubled. And the only reason we're writing it this way is to save space. That makes sense? Because in reality, is there such thing as half an oxygen molecule? No. So it's just a cheat. This would be the real reaction. I would prefer not to even teach you that because I think I personally think it's not bad form. It is definitely good form. It's allowed. It's permitted. But I think it's confusing because it makes you think that you're now allowed to start doing reactions with half of molecules, which you're not. This is just a math trick to avoid writing a more complicated solution. Yes?
But it's still work if you said like imperatives instead as well.
Sorry?
Like what if you did any fraction from the O2 to make it work?
Well, you would only ever have to divide by 2. Because the only problem with O2 is that it can't give you even numbers, or can't give you odd numbers, and dividing it by 2 makes it odd. So it would never be advantageous to do it by thirds or something like that. Just 2 is going to be the only thing that ever makes sense. But again, it's just a math trick. It is not describing something crazy happening chemically. It's just a math trick. Does that make sense? Would anyone like to share their combustions with me, what they came up with? Yeah, Zach Brown, what did you get?
Okay. I started off with 12 C3.
Wow.
I went off from 6.
Okay, hey, I like it. Okay.
So then I need, or should we write the whole thing out? And then
Yeah, just give it to me. Give me the whole thing.
33
How many?
33
Oh, good Lord. Okay, 33 O2s.
I put down 32 H2Os.
Nice.
12 CO2s. 10 carbon monoxide.
Wow. Can I say, that's a commitment. I like it.
started off with half that, but it's double it.
Yeah, I like it. Now, again, you could, in fact, if you prefer, write that as C6 here, 33 over 2 there. 16 here, 6 there, 5 and 1. But I like this better because, again, this to me makes more sense. But if you don't mind, I will write how you could write it just underneath, just to show you. So you could do 6 here, and this would have to be 33 over 2. This would be, and this would be, and this would be. Good. Does that make sense? Thank you. That's very complex. Yes. 3 of these, great. Plus 6 O2s.
Gives you 9, 1.
Yeah, 18, good.
3 CO2, 3 CO.
3 CO, yep.
Plus 2 CO.
Perfect.
Can I go back?
Yeah, of course. Very good. Anyone else want to share? Let's just make sure I'm sure they do, but let's just make sure the oxygen's balance. 9 and 3 more is 12. 6 times 2 is 12. Yep, oxygens look great. So that's a good balanced solution. Good job. Anyone else? Okay, so I'm going to give you the remainder of the period work, but I'm going to give you a couple of suggestion questions here, just ones to practice on. Give the complete and 2 incomplete combustions. Again, when we do complete combustion, what does that mean? Yeah, for complete combustion, we assume there's tons of oxygen and we just get CO2 and H2O. And how many possible answers are there? Just one. There's only one answer that works for complete combustion. But incomplete, you get to be creative. There's an infinite number of solutions. So give the complete and 2 incomplete combustions of, and I'm just going to give you some practice. Oh, not Beth. This is called butene. You don't have to be kidding. That last reaction should look real familiar to you, of course. Well, not photosynthesis, but that's the right idea, but the opposite, which is? The opposite of photosynthesis is? Come on, all you metabolic biochemists, ye. Photosynthesis opposite? Aposynthesis? Cellular? Cellular, not reproduction. Cellular respiration. Cellular respiration.
Cellular respiration.
That's right. Good job. You got it. Yeah, that was great. That was really good. Right? You learned that in grade 9 bio, you learned it again in grade 10 bio,
See, I
you
feel
learned it
like
again in
I
grade 11 bio.
I can't wrap my head around it. Like, it don't.
Oh, biology?
Yeah. That's why I didn't take it. But I knew I just didn't want to.
Do you know, so I was a biochemist, chemistry major, so I studied biology and chemistry. And I've got to teach chemistry a lot in my career, which I'm very thankful for, because I love chemistry. I've only ever got to teach biology once. And I just loved it so much. I loved it so much. I never again. Yes, ma'am? Yeah. Like mathematically what you're describing works, but that's not how. But like mathematically spot on. The math is good, but that's not the formula. Sorry. I know. Well, you get on. I have faith in you. Yeah. I can come to you if you give me the second. Just one. Oh, I'm going to get your lab books. Yeah, I'm going to do that. Yep, the complete combustion and then 2 incomplete combustions. Chemistry. Killer's not here. Kira's not here. Lauren's not here. I'm still recording, aren't I? Will I sing my attendance into the computer? Because I'm a professional. You know what?